You've probably heard it said that quantum mechanics and general relativity, our two most successful theories of nature, are somehow incompatible. That quantum mechanics, which governs particles and forces on the smallest scales, cannot be reconciled with general relativity, which shapes space, time and gravity on the largest. But what does that actually mean? Where does this tension reveal itself, and what happens when we try to make them work together? In this video, we're going to follow that clash to the place where it finally becomes unavoidable, when we try to treat gravity the same way we treat every other force in particle physics, using the tools of quantum field theory. To understand this problem, we'll first look at why quantum field theory works so spectacularly well for electromagnetism, and then we'll see what changes when gravity enters the picture, and why the same methods no longer work at the Planck scale. So buckle up and enjoy the ride. To begin with, we should recall what makes our existing quantum field theories, like quantum electrodynamics, so remarkably successful. Let's start with a simple example. In quantum electrodynamics, or QED for short, the probability for any particle process can be represented and calculated using Feynman diagrams. These diagrams encode information about the possible ways that a process can occur. For example, imagine two electrons that begin at points A and B and are later detected at points C and D. Even if there were no electromagnetic interaction at all, there are still two ways to connect the initial state and final state. The first corresponds to the situation where the electron from A ends up at C and the electron from B ends up at D. But another possibility is that A ends up at D and B ends up at C. Because electrons are indistinguishable fundamental particles, we cannot tell which of these two processes actually occurred. Quantum mechanics therefore requires that both possibilities be included. Okay, but what happens if we allow the electrons to interact with each other? The electromagnetic interaction between the two electrons arises from the exchange of a virtual photon. If one electron emits a virtual photon and the other absorbs it, we can draw a diagram showing this single photon exchange. In this diagram, if we imagine time running from left to right, we see that it was electron A that emitted the photon and electron B that absorbed it at a later time. But we could equally imagine the scenario where electron B emits the virtual photon and electron A absorbs it at a later time. In quantum electrodynamics, these two time-ordered pictures are not treated as separate processes. Both are captured by a single Feynman diagram for one photon exchange, which automatically includes every possible ordering of emission and absorption. The diagram doesn't show a literal sequence of events in time, it represents the sum of all such possibilities. Or to put this another way, the left-hand side of the diagram represents the initial state of our system, and the right-hand side represents the final state. The central part of the diagram carries information about the particles exchanged and the interaction vertices, but not the actual order in which those interactions occur. For example, in our diagram we have two vertices, and the particle being exchanged is a virtual photon. Now, it's important to realise that a Feynman diagram is far more than a picture of a process. It encodes precise mathematical information about the probability amplitude. Using the formalism of quantum field theory, one can extract a set of Feynman rules that translate each line and vertex into a mathematical expression. By way of example, let's look at the expression for this diagram. We begin by assigning momentum values to the incoming and outgoing electrons, and to the virtual photon that is exchanged. According to quantum electrodynamics, each vertex contributes a factor proportional to the electron's electric charge, while the incoming electrons and the outgoing electrons are described by spinors that represent their quantum states. The virtual photon connecting the two vertices also contributes its own mathematical factor, known as the photon propagator. We then multiply all of these terms together to obtain the amplitude for the process, and then the modulus squared of this amplitude is proportional to the probability that the process occurs. Now, for our purposes, the most important observation is that each vertex introduces a factor of e, the fundamental unit of electric charge. And so we see that in this basic Feynman diagram involving the exchange of one virtual photon, the amplitude is proportional to E squared. Because E appears as a factor at each vertex linking an electron to a photon, you can think of E as representing the coupling between electrons and the electromagnetic field. We'll have more to say about this shortly. Okay, so to very quickly summarise, each vertex gave rise to a factor of E, the fundamental unit of charge, and therefore the probability amplitude corresponding to this diagram is proportional to E squared. But this is not the only diagram that contributes to this process of two electrons interacting via the exchange of virtual photons. For example, we can also cross the external electron lines on the right-hand side of the diagram, producing another distinct but equally valid diagram. However, this new diagram still contains two vertices, and therefore its amplitude is also proportional to E squared. Now, the good news is that for single photon exchange, processes with amplitudes proportional to E squared, these are the only two diagrams we need to consider. These are known as tree-level diagrams, the simplest diagrams we can draw for a given process, in this case two electrons interacting via the exchange of virtual photons. But this naturally raises a question. Can we draw more complicated diagrams involving additional photons? The answer is yes. For example, we can have processes in which two photons are exchanged between the electrons, or processes in which one of the electrons emits a photon which it quickly reabsorbs, whilst also exchanging a separate photon with the other electron. There are also diagrams where an electron emits a photon, reabsorbs it later, and in the meantime exchanges a separate photon with the other electron. In these examples, we see a photon straddles the vertex. And then finally, there are diagrams in which a photon emitted by one electron temporarily converts into a charged particle-antiparticle pair. The pair then annihilates, producing another photon that is absorbed by the second electron. Now, what all of these particular diagrams have in common is that they each contain exactly 4 vertices, and therefore each diagram's corresponding mathematical expression will contain a factor of the fundamental unit of charge raised to the 4th power. Now, of course, we can also consider the corresponding crossed diagrams where the final electron lines are interchanged, and these also contain 4 vertices each. And so if we group all of these 4 vertex diagrams together, we have a collection of diagrams whose probability amplitudes are proportional to e to the power of 4. But of course, there's no reason to stop here. We can keep going and consider diagrams with 6 vertices, or 8 vertices, and so on. In fact, there is an infinite number of possible Feynman diagrams, each representing a different possibility for how the two electrons could interact between their initial and final states, involving the exchange of an even greater number of virtual photons. Finally, we can group the diagrams according to how many vertices each one contains, and then add them all together to obtain the total probability amplitude for the process. The first group contains 2 vertices, the second 4, the third 6, and so on. This means that the first group contributes terms proportional to e squared, the next contributes terms proportional to e to the 4, then e to the 6, and so forth. In this way, the final result can be viewed as a power series in the fundamental unit of charge, E. We can write this schematically in the following form, where mQED denotes the total amplitude, and the terms A0, A1, A2, and so on represent the combined mathematical contributions from all the Feynman diagrams at each corresponding order in the expansion. The squared magnitude then determines the probability that the process occurs, and in a scattering experiment corresponds directly to the measurable cross-section, or to the decay rate for decay processes. Now at this point, a few potential problems present themselves. First, the series contains infinitely many terms, so how can we possibly sum them all? Second, because the square of the amplitude maps to a measurable probability, our final prediction must be finite and well defined. Whether that happens depends on how the higher order terms behave. Do they shrink rapidly, or do they grow without bound? If each successive term increases rather than decreases, the series ceases to be useful, and the probabilistic interpretation of the theory would break down. So what determines whether the higher order terms are small or large? Well, ultimately it depends on how strong the electromagnetic interaction is. If the interaction is strong, then higher order terms involving the exchange of multiple photons could contribute significantly. We therefore need a way to quantify the strength of the electromagnetic coupling, to express in a single number how strongly an electron and a photon interact. And to do this, we start with something familiar: the Coulomb potential. When I'm researching for my physics videos, I always end up with too many tabs open. Research papers, YouTube videos, and articles from different sources. But recently I've started using the Opera browser, and honestly, it's made life so much simpler. One of my favourite features must be tab islands. I can group all my current tabs by topic or theme, like quantum mechanics, special relativity, and research papers. It keeps everything organised and far less overwhelming. I also love using split screen when I'm comparing data. Just drag a tab down and drop it next to the other. You don't need multiple browser windows. For example, having a research paper open on one side and a simulation or graph on the other. It's such a straightforward way to check information without constantly switching tabs. And this is where Opera's built-in AI tool, Aria, really helps. You can open it using Ctrl+/ or Command+/ and ask things like, group my IOP science tabs. It's like having a research partner built right into the browser. And one more thing I really like is the themes feature. You can fully customize the browser's look. I'm currently using the Aurora theme, but there are loads of options, so you can make it feel completely your own. Opera has become my go-to space for studying, writing, and creating all in one place. It's simplified my workflow and honestly saves me so much time. You can try it out yourself. Download Opera Browser for free using the link below or in the pinned comment. In electrostatics, the Coulomb potential energy corresponding to two electrons, each with charge E separated by distance r, is equal to 1/4 pi epsilon naught times E squared divided by r, where epsilon naught is the permittivity of free space. If we then multiply both sides by r, we find the expression Vr equals E squared divided by 4 pi epsilon naught. We note that the left-hand side now has units energy times length, and therefore for the units to balance, the right-hand side must also have units of energy times length. Now, in quantum field theory, there's a natural combination of constants that has exactly those same units. The clue lies in the fact that quantum field theory unites quantum mechanics with Einstein's special theory of relativity. The key constant in quantum mechanics is the reduced Planck's constant, h-bar, which has units of energy multiplied by time. The defining constant in relativity is the speed of light, which has units of length divided by time. Multiplying these two together gives h-bar c a quantity with units of energy times length, precisely the same combination we need. And so we can form a new dimensionless quantity equal to E squared divided by 4 pi epsilon naught divided by h bar c, which is equal to E squared divided by 4 pi epsilon naught h bar c. This number, known as the fine structure constant and denoted by the Greek letter alpha, has a value of roughly 1/137. It quantifies the intrinsic strength of the electromagnetic interaction on quantum scales. The beauty of expressing the coupling in this way is that alpha is completely independent of any system of units. And here is the key point. From the structure of alpha, we see that it's proportional to E squared. This means that the expression for the total amplitude we wrote down earlier, obtained by summing all the Feynman diagrams, can now be written in terms of the dimensionless constant alpha. You can think of alpha as effectively counting the order of interaction. Terms proportional to alpha describe the simplest single photon exchange diagrams. Those proportional to alpha squared include two photon exchanges or one loop corrections, and higher powers correspond to increasingly complex processes. And here is the crucial point. Because alpha is so small, the simplest processes contribute most to the final probability, while higher order terms are suppressed by additional powers of alpha. This is why QED works so extraordinarily well. It's a weakly coupled theory in which the lowest order diagrams already capture a lot of the physics with astonishing accuracy. And so, in summary, it's the fact that the dimensionless fine structure constant is so small that makes the whole perturbative system work. The weakness of the electromagnetic coupling strength ensures that the expansion behaves as a well-controlled asymptotic series in powers of alpha, where each additional set of terms provides small but important corrections that can be experimentally tested and verified. For example, QED's loop corrections famously explain the tiny deviation in the electron's magnetic strength, known as its anomalous magnetic moment. By summing thousands of Feynman diagram contributions across multiple loop orders, the theoretical prediction matches experiment to around 1 part in a trillion, the most precise agreement between theory and measurement in all of science. QED also explains the subtle energy shifts observed in hydrogen, known as the Lamb shift, which arise from the jittering quantum vacuum of electron-positron pairs and the electron's self-interaction with its own field. These are concrete payoffs of a weak coupling. The simplest diagrams dominate, the higher order ones are controllably small, and when we add them all, the numbers line up with reality to absurd precision. Now, it's worth saying that we've glossed over some important details. When we evaluate diagrams involving loops in quantum electrodynamics, it requires integrating over the momenta of the virtual particles. These integrals extend to arbitrarily high energies and, taken literally, produce infinities. If left untreated, the mathematics would predict infinite values for quantities such as the electron's mass and charge. The resolution is a process called renormalisation. In QED, these infinities can be absorbed into a small set of measurable quantities: the electron's mass, its charge, and the wave function normalization of the electron and photon fields. These parameters are fixed by experiment at a chosen reference scale, and all other predictions follow from them. After this redefinition, the theory remains internally consistent. Probability is conserved, and the expansion in powers of the fine structure constant alpha becomes predictive and remarkably accurate. There is, however, one further refinement. The fine structure constant is not truly constant. It changes very slightly with energy. The vacuum isn't empty, it teems with fleeting charged particle-antiparticle pairs that partially screen electric charge. At large distances or low energies, this screening makes alpha appear smaller, while at shorter distances or higher energies, the screening weakens and alpha grows. The change is modest. At atomic scales, alpha is around 1/137. Near the energies of modern particle colliders, it rises to about 1/128. And even if we extrapolate further, it only increases gently. Crucially, the change is only logarithmic with energy, so the coupling remains small and perturbation theory stays well behaved. In other words, the electromagnetic interaction remains weak over an immense range of energy scales, a triumph of the theory's structure. And so, in summary, QED succeeds because its coupling is small, its infinities are renormalizable, and its predictions remain precise across an enormous range of energies. It stands as the prototype of all modern quantum field theories, mathematically subtle, experimentally perfect, and still the most precise physical theory ever devised. So the question is, can we use this same approach to develop a quantum theory of gravity? Well, let's see how far we can get by following the same steps as before. For the case of gravity, the magnitude of the Newtonian gravitational potential energy for two masses m1 and m2, separated by a distance r, is g times m1 m2 divided by r, where g is Newton's constant. And if both masses are equal to m, we can write this as gm squared divided by r. Next, if we multiply both sides by r, we find Vr equals gm squared. And we see that both the left and right hand sides have units of energy times length, and so just as we did with QED, we can form a dimensionless constant by dividing the right hand side by h bar times c. In this way, we can define the dimensionless gravitational constant, alpha g, as gm squared divided by h bar c. And then, for the case of two electrons, we find a value of 1.75 times 10 to the minus 45. Now, the fact that this number is so tiny reflects the fact that gravity is an incredibly weak force at low energies and large distance scales. To make this explicit, if we compare the electromagnetic coupling with the gravitational coupling between two electrons and take the ratio, we find that electromagnetism is about 10 to the power of 42 times stronger at low energies. This explains why gravity is essentially irrelevant in atomic physics and in particle collisions at current accelerator energies. Now, at first sight, you might think, great, an even smaller coupling than in QED, so a perturbative Feynman diagram approach should work beautifully. However, in Einstein's general theory of relativity, gravity doesn't only respond to mass at rest, it responds to energy in general. At high energies, the gravitational effect of a particle is therefore set by its total energy, not just its rest mass, essentially by how energetic the interaction is. The connection between energy and mass is provided by Einstein's famous equation E equals mc squared. If we rearrange this expression for m, we can then sub this into our expression for the gravitational coupling strength, and we end up with the following expression. And if we then simplify, we find that the gravitational coupling can be written as ge squared divided by h bar c to the power of 5. And this is now expressed in terms of energy rather than mass. Now, here's where things get really interesting. There exists a special combination of constants, h bar, c and g, that defines a fundamental energy scale in nature. It's called the Planck energy, and it's given by the following expression. I encourage you to check that this combination of constants does indeed have units of energy. Now, numerically, this corresponds to an energy of order 10 to the power of 19 gigaelectronvolts, which is breathtakingly large, roughly 900 trillion times higher than the energies reached at the Large Hadron Collider. And the remarkable thing is that we can now re-express our gravitational coupling in terms of the Planck energy. If we combine our expression for alpha g with the Planck energy, the entire expression for alpha g collapses beautifully into a single simple ratio, E divided by EP, all squared. And this is what we were looking for. This is the gravitational coupling strength, but something truly shocking has emerged. Unlike the fine structure constant in QED, which stays small and only changes very slightly with energy, the gravitational coupling grows as E squared. That means that as we push to higher and higher energies, the coupling strength grows rapidly. If, for example, we consider LHC collision energies of order 10 to the power of 4 gigaelectronvolts, this gives a gravitational coupling strength of order 10 to the minus 30, a tiny number, effectively zero, and an indication that quantum gravity effects are negligible at current collider energies. But as the energy approaches the Planck energy, the coupling strength approaches 1. That's the moment when our perturbative Feynman diagram approach, the very framework that makes QED so powerful, begins to fall apart. This doesn't mean physics itself fails at the Planck scale, only that this particular perturbative method stops being the right tool. To see this, let's translate this into a diagram expansion for gravity in exactly the same spirit as we did for QED. Now, the gravitational field's hypothesized quantum is called the graviton. This is the analogue of the photon being the quantum of the electromagnetic field in QED. The simplest scattering diagram has two energetic particles exchanging a single virtual graviton. That contribution carries one factor of the effective coupling alpha g. Diagrams with additional exchanges or loops bring extra factors of alpha g. We can then imagine grouping diagrams according to the power of the coupling, just as we did for QED. When we do this, we end up with the power series expansion in alpha g of the following schematic form, where m gravity is the total amplitude and b0, b1, b2 and so on represent the combined mathematical contributions from all the Feynman diagrams at each corresponding order in the expansion. Then, by looking at the structure of the gravitational coupling, we see that at low energy, alpha g is so tiny that the first term dominates, and loop corrections are massively suppressed. However, as the energy approaches the Planck energy, alpha g approaches 1, and the hierarchy collapses. One loop, two loop, and higher loop diagrams all contribute with equal weight, and higher order terms are no longer small compared with the first term. In other words, the tidy tower of Feynman diagrams that work so perfectly for QED comes crashing down. Every correction becomes as large as the last. There's no small number left to keep the mathematics under control. Beyond that point, the very logic of perturbation theory, the idea that we can understand nature by adding smaller and smaller corrections, simply breaks. But the problems don't stop there. In QED, the infinities that appear in loop diagrams can be absorbed into just a few measurable quantities, as we've already seen: the electron's mass, its charge, and the wave function normalisation of its fields. Once these are fixed by experiment, the theory remains predictive and consistent at every order. Gravity, however, behaves very differently. When treated as a quantum field theory, it produces new and increasingly severe divergences at higher loop order. These cannot be absorbed into a small finite set of parameters. Each new level of correction introduces new kinds of infinities that would require new counter terms to cancel them. And because an infinite number of counter terms would need to be fixed by experiment, the theory loses its predictive power if we demand it works at arbitrarily high energies. Formally, gravity is described as perturbatively non-renormalizable. Now, in practice, this only becomes serious at extremely high energies, where the gravitational coupling approaches 1. On the other hand, at low energies, quantum gravity works beautifully as an effective field theory, giving tiny, well-controlled corrections to classical gravity. For instance, one can calculate small quantum corrections to Newton's law of gravitation. The potential between two non-relativistic point masses is found to take the following form, where the first correction comes from general relativistic effects, while the term proportional to h bar is the genuine quantum gravity contribution. These results arise entirely from the low energy part of the theory. They are not guesses about the Planck regime, but concrete testable predictions of quantum gravity in the weak field limit. These corrections are unimaginably small for ordinary masses, which is why they have not yet been measured experimentally, and why they are essentially unimportant at low energy scales. And so a clear and subtle picture emerges. Quantum gravity does work, well, at least at low energies, giving small testable corrections, but because the gravitational coupling grows with the square of the energy, the perturbative method that makes quantum electrodynamics so successful breaks down at the Planck scale. So what is this really telling us? What is the significance of the Planck scale, and why does perturbation theory fail here? Well, the key point is this. The breakdown at Planck energies does not mean that physics itself collapses. It simply means that the mathematical tools we've been using are no longer appropriate. Nature isn't breaking, our method is. As Nima Arkani Hamid put it, attempts to make sense of quantum mechanics and gravity at the smallest distant scales lead inexorably to the conclusion that spacetime is an approximate notion that must emerge from more primitive building blocks. And this is what we'll explore in the next video, from black hole limits on measurements to the generalized uncertainty principle to the possibility that spacetime itself might be emergent. The Planck scale isn't the end of physics. It's the edge of the map. But for now, thank you for listening, and until next time, goodbye. And as always, a massive thank you to all my patrons, and a special shout out to the following who have been incredibly generous with their support. Thank you so much. I couldn't do it without you.